Welcome to a quick review of simple harmonic motion. I need to get ready for the AP Physics B exam. What we're going to look at here in simple harmonic motion, if you remember from your studies, is this would be the motion of an object, let's say, that's going up and down in some sort of a repeated motion. In this case right here, we might have a ball that's on a spring. Let's say for ease of discussion that we're looking down on this and it's on a flat table. You've had this ball in which the spring has been compressed. The ball is released and it kind of has this, let's say this initial velocity in this direction once it's released. The ball goes through kind of what would be the unstretched position of where the spring would have been. We call that the equilibrium position, something like this. And the ball goes all the way to, let's say, the opposite side to a fully stretched position on the other side. And then we can start asking certain questions about the arrangement here. We give certain terms to these different things. One is this kind of displacement away from equilibrium in this case. We give the term A for amplitude. This is the largest displacement from equilibrium that the mass makes. As this thing goes back and forth across these positions, we can ask questions about its velocity, let's say, or its acceleration. In this case right here, you can kind of see that if it's released at this initial position right here and starts traveling in the other direction, it's going to have its greatest value for its velocity as it goes through this right here. You're going to have some kind of a V max as it goes through here. And notice that the velocity will be equal to 0 at each of the turnaround points. You'll have a velocity 0. You could also see here that based on this motion here, that this thing is going to be, if we did a motion diagram for this, for instance, it would be, let's say after it got this portion right here, it would start slowing down in this direction. So therefore it must have an acceleration that's acting in the opposite direction, in this case right here, an acceleration in this direction, kind of an acceleration towards our equilibrium point. You can see it may be a little bit harder to see why this would be the case, but your maximum accelerations are going to occur at these outer limits. So you'll have your acceleration max will occur here, where the velocity is changing from first being in like one direction and then being in the opposite direction. That actually gives you the biggest change in velocity, acceleration max there. Very little acceleration or 0 acceleration as the object goes through its equilibrium point. These accelerations point out that the object is experiencing a force, of course, and so we can be specific about the force in this case. The force is being applied by the spring, and so we have an equation associated with that. The force of the spring is equal to minus, which is really just a placekeeper for the direction of the force, times a spring constant times this displacement from equilibrium. I'm going to box that so you remember that this is one of our equations on the equation sheet. Now you can see based on the little discussion that we've done so far, the force in this case is going to be greatest where the displacement is greatest. And since the force will be greatest there, you can expect your maximum acceleration there. The force will be minimum, or in fact 0, as the object goes through the equilibrium point, and therefore acceleration therefore is 0. So it should make sense the things we talked about with acceleration should coordinate with this equation for the force on an object that is attached to a spring. Now the very fact that this force is continually changing, in other words, you can kind of see here as the displacement gets greater and greater, the force gets greater and greater. That means the acceleration must also be changing, which means we cannot use, and this is an important point to make, we cannot use motion equations to solve for the motion for objects in simple harmonic motion. But we can, in fact, use energy. Energy allows us to answer motion questions about this object going back and forth around this point here. So if we wanted to analyze this situation, for instance, associated with energy, then we can come up with a couple terms. Of course, there's going to be an initial kinetic energy, let's say. Let's use this initial point here where it's initially released. So what we'll do here is we'll analyze First, this situation right here, we'll say it's initially released at rest right there. So let's say it has some kind of term associated with kinetic energy. It has some potential energy because of gravity. It has some potential energy because of the spring, for example. Maybe there's friction in the problem, so there might be plus or minus work done. And that'll have to equal the kinetic energy for this whatever next point we choose, the potential energy for gravity for whatever next point we choose, and potential energy because of spring for whatever second point that we choose. And you can kind of see, like we did for in conservation of energy in general, let's say this thing does not start out with any initial kinetic energy. Let's say that this is a flat surface and we can disregard the gravitational potential energy. But let's say, since in this case the spring has been compressed, that this thing has been loaded up with a certain amount of energy. We'll call this frictionless, so we won't have any work. And let's say we're interested in our second position here, which would be, let's say, this position right here, something like that. We could say that in this case the gravitational potential energy and spring potential is zero, going through equilibrium. And you can kind of see here how you could use the energy bar graph in this case to solve questions about the motion of the object. We have equations associated with each of these. For instance, the kinetic energy is our 1/2 mv, this would be v2 squared. And we also have an energy equation associated with spring potential. And I'll write that down here because it's related to our overall thing that we're pumping up here, is spring potential energy. And that number right there is going to be equal 1/2 k times our displacement from equilibrium squared. I put a box around that because that's another one of the equations that we have on the equation sheet. All right, now the next thing that we can talk about, one more thing we can talk about for this thing going back and forth that's not really captured by our energy, is we can also ask how much time does it take, let's say, to make one full cycle back and forth. And our relationship associated with the time that it takes here for simple harmonic motion is simply this equation for the period of a spring. So really this is the equation for this period of an object attached to a spring, and it's equal to 2 pi times the square root of the mass of the object divided by the spring constant. And that is also on your equation sheet. Now that equation should make sense. As I increase the mass of the object, it gets more sluggish, kind of going back and forth. So it should make sense that if I increase that number, I'll increase my amount of time, my period. If I increase k, then I'm increasing the tightness of the spring. So the spring is it's springier. So if I increase that, I should expect actually a shortening of the period of time, and that makes sense from the equation that we have right here. Now if I zoom out here, we can think of, in this case right here, I've taken a look at kind of some physical attributes to the system of an object on a spring. Sometimes this can be shown in graphical format as kind of a displacement with respect to time graph. So in this case, I'll keep it the same. Let's say I release it at some kind of a point here. And now what I'm going to say is over time, this thing is going to vibrate up and down, something like this. So what I'm looking at on this axis right here in this graph would be time going in the positive direction this way. And over here, some kind of displacement from equilibrium like that. You can kind of see if these problems are given in this format, then this sort of a distance right here, in other words, my maximum displacement distance, you can kind of see, this is a graphical sort of thing now, is my amplitude, that number right there. And you should be able to see now that the distance between the two crests here, you have to be a little careful thinking here, because sometimes we think of distance between two crests as wavelength. But in this case, it's not a wavelength because we're looking at time on the horizontal axis. So this is the time for an entire cycle, which of course is our period. And so that's how you can get that period by being given a position with respect to time graph. These position with respect to time graphs for an object that's in periodic motion actually operates just like any position graph, time graph that we've used before. So for example, choose any point here. Let's say I'll use this point down here. If I want to know information, let's say the velocity at that point, what I would do is just like I would do on any position with respect to time graph, I could find that tangent line. The tangent line would give me this change in position with respect to time on this graph, which is, in other words, another way to get the velocity. In other words, the instantaneous velocity I can get at any point. And you can kind of see with this case right here, if you think of this as a ski kind of going along this this curve, you can kind of see it has the steepest velocity in this case right here. This velocity, if I were to measure it down here, would have a slope of 0, and that's what we said before, the velocity would be equal to 0. You can kind of see using this information, you can get information about velocity. You could also, a little trickier, be able to get information about acceleration, because how fast this slope is changing. So for instance, if we come down here and we say, in this short period of time here, the slope might be here, and then the slope is here, and then the slope is here. You can kind of see that's a pretty quick change in slope, but a pretty quick change in slope, of course, is a large acceleration. So that's telling you the acceleration is a maximum at those points. So everything you know about position with respect to time graphs applies to these sort of graphs. I should notice one more equation that I guess that is another way to capture this idea of the amount of time or the period, and that is this this other term which is associated with frequency. So this period here is equal to 1 over our frequency. And we can think of frequency not just like frequency of light, we can think of frequency of any oscillation, and that's how we can go back and forth between those two numbers. Now this example here of the wave that I've just drawn here, of course, could be written out as some sort of a wave equation. In other words, some sort of a displacement over here would be equal to, you can pretty clear that this would be like either a sine or a cosine wave. It's actually not important whether you designate this as a sine or a cosine wave, because you can just use phase shift to figure it out. But you can kind of see in this equation here that this number right here would have to be multiplied by my amplitude, and there's got to be some kind of a number times t, since t is my horizontal variable on the axis here. And what is placed here right here is some sort of a number associated with the time, and in this case it's this omega. Now I want to be kind of clear here. So this is this basically thing right here that I've just drawn is the equation for a sine wave. And this number, this multiplier times my t, is something that's important. And in this case right here, this omega is equal to 2 pi times the frequency. And that's called an angular frequency, and it's just the way this works out. The 2 pi conversion has to do with keeping this in radians. So that's the general form for a sine wave for all simple harmonic motion. Okay, so what I'd like to do now is go to our one other, I guess what I'll go ahead and break the presentation here, and I'll pick it up on the other side, and we'll take a quick look at pendulums.